So just before starting the Arrhenius equation, just make sure you're happy with logs and how they work, and log to base e, because that's what the Arrhenius equation uses. Now, the Arrhenius equation is a guy called Arrhenius who's done like quite a large mathematical derivation. And so this is, getting a little bit like the SPDFs, and it's sort of the high level chemistry is really starting to get very physics-like, and so basically I'd ask you to do is to be able to use its equations. So that's an Arrhenius factor, so that's a common factor. So it's the likelihood that collisions would occur at the proper orientation for a reaction. Probably learn that as a definition. Activation energy, temperature, gas constant, Okay, so in your syllabus, it does want you to know that the rate constant is directly related to temperature. And I leave these guys to do the calculation. So this one's increasing in 10 degrees Celsius, and the rate constant sort of doubles. Okay, so that was just a good rule of thumb. If you want to double the rate of a reaction, just increase it by every 10 degrees and it doubles. That's a rule of thumb. Okay, so just be able to use the equation. And the only thing you really need to know is y equals mx plus c. So what you're really trying to do is find out what the activation energy is. So you'll be given lots of data. You just have to convert the k's to using natural logs. So you get the y. You're not even going to worry about the Arrhenius factor. And then you're going to invert the temperature one on T to get the x. And then this left over, the gradient, will give you this. And that's a constant. So the gradient will be able to tell you, subbing that into a reaction, will be able to tell you what the activation energy is. So basically just realize that equation in the data booklet is y equals mx plus c. Set it up with all the data. So you've done a graph of natural log of k, rate constant, and 1 on t. Grab the gradient, sub it into that equation, m equals minus ea over rt. M equals minus e over r, and you're done. Okay, so just quite painful. And so there it is again. So there you can see the gradient is this. You've changed all the values to this, and it must be Kelvin, of course. Okay, so convert all the rate constants to K, do natural logs, do this in our table. All the temperatures to Kelvin, one divided by that. Draw up the graph, find the gradient, m equals this, and therefore you'll be able to solve what EA is. A lot of work. Okay, so here's a practice question, and that's it. I'm just going to leave it there. I expect that you will take a long time to do this, at least half an hour, maybe the whole lesson. All right, and then when you're done, go have a look at the answers. Okay, so you can stop there. Okay, so I'm going to continue now because you've spent the whole lesson doing this, and hopefully you've come up with this. The temperature's already been converted to Kelvin for you, which is nice. And so the K's are here. All right, so I need to do a natural log of I need to do the 1 on T's and a natural log of the K. So I need to do another. So this is the bit I have to do. So redo these values and then log them. That's the Y, that's the X. There you go. There's the Y, that's the X. There's the gradient. Work out what the gradient is. The gradient's this. All right, and that's EA on R. Okay, so there it is, sub it in. 102 kilojoules per mole, how'd you go?